Download this code from codegive.com, link in the description below. Kernel Recipes 2022, IO_Uring's Path to Zero Copy IO, a deep dive tutorial. This tutorial delves into the evolution of IO_Uring in the Linux kernel, focusing on its journey towards zero copy IO. We'll explore the concepts, functionalities, and code examples that illustrate how IO_Uring achieves significant performance gains by minimizing data copying between kernel and user space. This tutorial builds upon the concepts presented at Kernel Recipes 2022 and provides a comprehensive guide to understanding and leveraging zero copy IO with IO_Uring. Why zero copy IO? Traditional I/O operations often involve multiple data copies between user space buffers and kernel space buffers. This adds overhead, consuming CPU cycles and memory bandwidth. Zero copy I/O aims to eliminate these unnecessary copies, allowing data to move directly between the storage device, or network, and user space. This can lead to substantial improvements in I/O-bound applications, particularly those dealing with large datasets, network services, and database systems. IO_Uring, a modern I/O interface. IO_Uring is a relatively new I/O interface in the Linux kernel designed for high-performance asynchronous I/O. It offers several advantages over older interfaces like ePOL and DAIO, including asynchronous by design submits I/O requests to the kernel without blocking the application. Kernel side scheduling the kernel manages the scheduling and execution of I/O operations. Ring buffers uses two ring buffers, submission queue, SQ, completion queue, CQ, for efficient communication between user and kernel space. Polled IO supports polling for IO completion, reducing context switching overhead. Zero copy potential provides mechanisms to minimize or eliminate data copying. Key concepts for zero copy with IO_Uring*. 1. IOring_setup_skpol, kernel polled submission. When enabled, the kernel actively polls the submission queue, SQ, for new requests, reducing latency compared to traditional interrupt-based submission. This is crucial for minimizing context switching and maximizing performance. 2. IOring_setup_IOPOL, interrupt polled completion similar to skpol, but for completion events. The kernel polls the device directly for completion notifications, bypassing interrupt handlers. 3. IOring_register_buffers, fixed buffers allows registering a set of pre-allocated memory buffers with the IO_Uring instance. I/O operations can then reference these buffers by index, avoiding the need to pass buffer addresses with each submission. This is a foundation for zero copy. 4. IOring_op_read_fixed and IOring_op_write_fixed. Fixed buffer I/O. These operations use the pre-registered buffers specified by IOring_register_buffers. The kernel can directly read from or write to these buffers, effectively eliminating data copies if the underlying device supports direct I/O, DIO. 5. IOring_op_provide_buffers and IOring_op_get_buffers, scatter/gather list, SG list, I/O, provides a mechanism for handling I/O with non-contiguous memory buffers. This involves registering a pool of buffers, and submitting requests to dynamically acquire and use these buffers for read/write operations. This can be a more complex, but very powerful, zero copy option. 6. IOring_op_sendmsk and IOring_op_readmsk with message_zero copy, zero copy network I/O for network operations. The message_zero copy flag allows direct transfer of data between user space and the network card, bypassing kernel buffers. This is primarily applicable to TCP sockets. Code example, zerocopy read with Uring_op_read_fixed. This example demonstrates a zerocopy read using Uring_register_buffers and Uring_op_read_fixed. Explanation asterisk. 1. Initialization asterisk. The code initializes the IO_Uring instance and opens the file. Crucially, it opens the file with O_direct flag. This flag bypasses the kernel's page cache and forces the I/O operations to go directly to the underlying storage device. Without O_direct, zerocopy is not possible with Uring_op_read_fixed or Uring_op_write_fixed. 2. Buffer allocation and registration asterisk. Asterisk *p6_mammalian is used to allocate memory that is page aligned. Page alignment is a requirement for O_direct I/O. Asterisk. The allocated buffers are registered with the IO_Uring instance using IO_Uring_register_buffers. We pass an array of IOVEC structures, each describing a buffer and its size. The BGID, buffer group ID, is set to 0. This allows using a single buffer group. 3. Submitting read requests asterisk. Asterisk IO_Uring_prep_read_fixed, prepares a submission queue entry, SQE, for a read operation using the registered buffers. Asterisk FD, file descriptor. Asterisk buffers buff_index, points to the memory location where data will be read. However, since we have registered buffers, this isn't used directly for the read address, instead the buff_index is. Asterisk read_size, the number of bytes to read. Asterisk offset, the offset in the file to read from. Asterisk buff_index, the index of the registered buffer to use for this read. This is the key element for zerocopy using fixed buffers. The kernel knows to use this registered buffer. Asterisk SQE-user_data, we store the offset in the file as user data, useful for debugging or verification. Asterisk. The requests are submitted to IO_Uring using IO_Uring_submit. Asterisk. The code cycles through the registered buffers to avoid overwriting data that hasn't been processed yet. 4. Completion handling asterisk. Asterisk IO_Uring_wait_, waits for completion events to arrive in the completion queue, CQ. Asterisk. The CQE-res field contains the result of the operation, number of bytes read or an error code. Asterisk. The code verifies the result and processes the data in the buffers. Asterisk IO_Uring_seen, marks the completion queue entry as processed. 5. Cleanup asterisk. The code unregisters the buffers, frees the allocated memory, closes the file descriptor, and exits the IO_Uring instance. It's vital to unregister buffers before freeing the memory. Important considerations for zerocopy asterisk. Asterisk O_direct asterisk. As mentioned, O_direct is essential when using Uring_op_read_fixed or Uring_op_write_fixed for file I/O. Without it, the kernel's page cache will still be involved, and data will be copied. Asterisk alignment asterisk. With O_direct, you must ensure that asterisk. The file offset is aligned to the file system's block size, typically 512 bytes or 4096 bytes. Asterisk. The buffer address is aligned to the page size, typically 4096 bytes. Asterisk. The read/write size is a multiple of the file system's block size. Asterisk. You can determine the block size using statfs, or ioctl, fd, bgazkit. Asterisk. Memory allocation asterisk. Use *p6_mammalian, to allocate memory that is correctly aligned for O_direct.
Asterisk performance tuning asterisk experiment with different Uring setup flags, Uring setup skpal, Uring setup iopol, and queue sizes to find the optimal configuration for your workload. Code example, zerocopy network IO with message _zerocopy. This example shows how to send data over a TCP socket using the message _zerocopy flag. Explanation asterisk. 1 socket setup asterisk standard socket creation, binding, listening, and accepting a connection. The new socket is set to non-blocking. 2 message _zerocopy asterisk. The crucial part is using Uring prep send with the message _zerocopy flag. This tells the kernel to attempt a zerocopy send operation. 3. Send the message asterisk. A send structure is prepared and passed into the Uring prep send. 4. Completion handling asterisk. The code waits for the send operation to complete. Important considerations for message _zerocopy asterisk. Asterisk kernel support asterisk. Message _zerocopy relies on network card driver support. Not all drivers support it. If the driver doesn't support it, the kernel will fall back to a regular, copying, send operation. Asterisk TCP only asterisk. Message _zerocopy is primarily applicable to TCP sockets. Asterisk memory pinning asterisk. The kernel might need to pin the user space memory pages containing the data to prevent them from being swapped out while the DMA transfer is in progress. This can consume memory. Asterisk performance asterisk. While message _zerocopy can improve performance in some scenarios, it's not always a guaranteed win. The overhead of memory pinning and driver support can sometimes outweigh the benefits of avoiding data copying. Benchmarking is crucial. Asterisk error handling asterisk. The application needs to handle potential errors related to message _zerocopy failing to allocate resources or perform the zerocopy transfer. Using Uring op provide buffers and Uring op get buffers, sglist.io. This pattern allows for more flexible buffer management, useful when you have many smaller, non-contiguous buffers. 1. Register a buffer pool asterisk. Allocate a pool of buffers and register them using Uring register buffers. 2. Submit Uring op provide buffers asterisk. Whenever a buffer in the pool is free, submit an Uring op provide buffers request to return the buffer index to a buffer group. This makes the buffer available for use in subsequent I/O operations. 3. Submit Uring op get buffers, instead of regular I/O. Instead of submitting a regular Uring op read or Uring op write, submit Uring op get buffers. This request signals that you need a buffer from the specified buffer group. You specify the amount of data you plan to read/write. 4. Completion of Uring op get buffers asterisk. When the Uring op get buffers request completes, the CQE-res will contain the index of the allocated buffer. The CQE-user_data could contain an ID to identify this buffer request. The request could also fail, be negative, if there are no buffers available. 5. Perform I/O with the acquired buffer asterisk. You now have a buffer index and can use Uring op read fixed or Uring op write fixed with this index to perform I/O to/ from the acquired buffer. 6. Return the buffer asterisk. When you're finished with the buffer, submit Uring op provide buffers again to return it to the pool. This pattern is complex but offers significant flexibility for managing buffers in high-throughput scenarios. It's commonly used in network packet processing where incoming data needs to be distributed across multiple buffers. Beyond the basics,
performance considerations and best practices asterisk. Asterisk benchmarking asterisk always benchmark your code with and without zero copy techniques to ensure that you are actually achieving performance gains. The overhead of O_direct, memory pinning, or complex buffer management can sometimes outweigh the benefits. Use tools like FIO and IPRF to measure I/O throughput and latency. Asterisk NUMA awareness asterisk if your system has non-uniform memory access, NUMA, architecture, ensure that you allocate memory buffers on the same NUMA node as the CPU core that is performing the I/O operations. This can reduce memory access latency. Asterisk CQE processing asterisk optimize the way you process completion queue entries, CQEs. Avoid unnecessary memory allocations or calculations within the CQE processing loop. Asterisk error handling asterisk implement robust error handling to gracefully handle failures related to I/O operations, memory allocation, or device errors. Pay special attention to errors returned in the CQE-res field. Asterisk kernel version asterisk the functionality and performance of IO_Uring have improved significantly over time. Use a recent kernel version, 5.10 or later, for the best results. Check the kernel documentation for the latest features and bug fixes. Asterisk IO_Uring_enter, asterisk while the higher level IO_Uring_submit_an_wait, is available, for advanced use cases, understanding the underlying IO_Uring_enter, system call is essential. It gives fine-grained control over the submission and completion process, enabling features like busy waiting and custom polling strategies. Asterisk SQ thread asterisk for high throughput applications, consider dedicating a separate thread to submitting requests to the submission queue, SQ. This can improve performance by reducing contention between the submission and completion threads. Asterisk avoiding deadlock asterisk be very careful to avoid deadlock scenarios. If you have multiple threads submitting requests to IO_Uring, ensure that the submission and completion processes are properly synchronized. For example, if you're waiting for a particular request to complete before submitting another, ensure that the completion handler is always executed, even if an error occurs. Conclusion asterisk. IO_Uring provides a powerful and efficient interface for asynchronous I/O in the Linux kernel. By leveraging features like fixed buffers, message_zerocopy, and scatter/gather lists, you can minimize or eliminate data copying, leading to significant performance improvements in I/O bound applications. However, zero-copy I/O is not a magic bullet. It requires careful planning, coding, and benchmarking to ensure that it actually delivers the desired performance gains. By understanding the concepts and techniques outlined in this tutorial, you can effectively leverage IO_Uring to build high-performance I/O applications. Remember to benchmark thoroughly and choose the best approach for your specific use case. Good luck.